Differential equations is the new chapter for the session. So what is a differential equation? As we know that derivative or differentiation is from which we derive the differential equations. So now that we have derived about differentiation and integration when combined together gives us the process of solving differential equations. That means in order to solve the differential equations, we use both differentiation and integration. As the word itself says, differential equation, an equation which involves derivatives is called a differential equation. To see the more mathematical definition, let's continue with the session. Now let's see the more mathematical definition of differential equation. Differential equation is defined as an equation which involves one dependent variable and one or more independent variables is called a differential equation. That is, when we see that a differential equation should have one dependent variable or it can have one or more independent variables. So let's see with an example what is a dependent variable and an independent variable which combine to form a differential equation. Say for example, I have now here I clearly see that this is a differential equation because y depends on x, that is derivative of y with respect to x. Here we have y which depends on x. Therefore, the dependent variable here is y and the independent variable here is x, which is written in the form of an equation involving derivatives. So this is a differential equation. A differential equation with one dependent variable and one independent variable is how we understand the basic mathematical definition of differential equation connected with derivatives. Now let's take another example where I have x dy by dx plus z d square y dy by dx whole square minus 3 z square equal to 0. 3z square x equals 0. Now this is a differential equation where I have the dependent variable which is y, but there are two independent variables x and z. So in this case, the dependent variable is y and the independent variables are x and z. Is how we understand the difference between dependent variables and independent variables for the given differential equation. For a differential equation, there is only one dependent variable, but it can have one or more independent variables. Only one dependent variable. Now next, let's see the types of differential equations. Now that we have discussed about differential equations, now let's see the types of. Now there are two types of differential equations through which we classify the dependent and independent variables. So the first is ordinary differential equation, and the next is partial differential equation. So for ordinary differential equation, we have the condition it has only one independent variable. But when you take the partial differential equation, it has more than one independent variable. Is how we differentiate between the ordinary differential equation and the partial differential equation. One independent variable, the equation is called ordinary differential equation, and more than one independent variable, the differential equation is called partial differential equation. For example, x dy by dx whole square minus e power x dy by dx equals 3 is an ordinary differential equation because we have one dependent variable y and only one independent variable x. Here x is the independent variable. Now in case of this, now this is with one dependent variable z, but there are two independent variables x and y. So in this case, it has more than one, and hence it is called partial differential equation. So usually the derivatives in partial differential equation are denoted with dou by dou z or dou by dou x is called partial differential equation, and d by dx of a function is denoted for ordinary differential equation. So dou by dou x for partial differential equation and d by dx for ordinary differential equation is how we understand the difference between ordinary differential equation and partial differential equation. One independent variable, partial ordinary differential equation, more than one independent variable, partial differential equation. The next concept is degree of a differential equation. What is the degree of differential equation? So as we have discussed about the differential equation, let's see in the session about degree of a differential equation. So here we define the degree as the integral power of the highest derivative term. This is the most simple definition which we have considered. Let's try to understand this more better through a live example. So integral power of the highest derivative term. For example, if I take x d cube y by dx cube minus 3 dy by dx is equal to 4 d square y by dx square whole power 4 by 3. So clearly this is a differential equation with independent variable y and the dependent variable x, and of course this is an ordinary differential equation involving only one independent variable x. Now let's see what is the degree of this differential equation. Now the definition which we have taken here is integral power of the highest derivative term, that is I take the integer form of this, that is if I take the highest derivative term is this, its integral power is 1, but we don't take fractions considered. The rule is that we eliminate the fractional part of other derivatives. In order to delete this with fraction, I cube on both sides, and therefore I get this term to be x whole cube is 4 d square y by dx square whole power 4, because 1/3 comes here as cube. So cubing on both sides I get this, therefore now this is reduced to integral powers, and hence the highest power of the highest derivative, which is d cube y by dx cube, is 3, and hence the degree of the given differential equation is 3. So degree is 3 for the given ordinary differential equation. Let's practice some problems in finding the degree of the given differential equations. So using the definition, now this is the differential equation whose degree I need to find. So clearly I see that the degree of this differential equation is, with the highest degree, the highest derivative is 2, but it has the power as 3, but this is in the form of fractional root, which can be squared on both sides so that this gets multiplied twice. So in order to make this an integer, we multiply both sides with 2. I mean, we take squaring on both sides of the equation, and this gets multiplied with 2, and this becomes an integral part, and therefore 6 would be the degree. So degree of such a differential equation would be 6, is how we do. But ultimately it is very important that we make each of them with non-fractional power. Let's try one more example problem. So this kind of a problem where we try to find the degree, we try to just take this to the numerator by cross multiplication, then the highest derivative is d square y by dx square. So here this is d square y by dx square, this gets multiplied with this to get 3. So on cross multiplication I get d square y by dx square whole power 3, but again I have this non-fractional. To make this an integer, I multiply with 3 or cube on both sides, so this gets reduced to 3. Therefore in this case, in order to maintain that this is an integer and this comes to the numerator, I have this as 9. So the degree is 9 for the given differential equation is how we understand the degree and order of a differential equation. The order of a differential equation. Now, as we see this problem, as we see this concept of order, it is nothing but derived from degree of a differential equation. That is, the highest, the integral power of the highest derivative, or the highest derivative of a differential equation is called order. So here, the highest derivative of a differential equation is the order of the differential equation. That is, for example, if I take x dy by dx minus 4 dqy by dx cube is equal to 7 minus 3 e power x so clearly I see here that this differential equation has the first derivative here, third derivative and seventh derivative. As I see, the highest derivative of this differential equation is 7 because it has the 7th degree differential part of y. Therefore, order of this is 7, and of course my degree is nothing but the power of the highest order, that is degree is 1, because the rest of the derivatives are all integrals, not fractions. Therefore degree is 1. So order is 7 and degree is 1 is how we understand this. Now let's see another example problem through which we understand the order and degree of a differential equation more better. So for example, I have this equation. Then how do we find order and degree? Now, as we have each of them with fractions, this fraction gets eliminated through 0 because raising to the power 4, this becomes power 1 because 4 vanishes when multiplied with 4 on both sides. Now the next task is making them as integers. Therefore, clearly I see that order of this differential equation is 2 because this is the highest derivative, and the power of this to be made an integral value, I have to just multiply the two equations with 6, because when you multiply both of them with 6, it becomes an integer and this becomes an integer. And therefore, the highest power of the highest derivative is 2. And therefore, I get my degree is power of the order, that is 2, which I get as 3 1s, 3 2s, and hence order is 2 and degree is 2 for the given differential equation is how we understand order and degree of a differential equation connected. Now that we have discussed about order and degree of a differential equation, let's see the limitations which the differential equations have. Now the limitations of the order and degree of a differential equation is that degree of a differential equation, as we have seen in the previous case, is defined only if the degree of a differential equation is defined only if the differential equation is a polynomial differential equation. If you cannot express the differential equation in the form of polynomial differential equation, then the degree is not defined. For example, I have the differential equation x d square y by dx square minus 4 e power x dy by dx equals log dy by dx. Then we cannot find the degree of this. Though the order is the highest derivative, the order of this differential equation is 2, but degree is not defined because of log. This cannot be expressed as a polynomial differential equation. That is, since the given differential equation cannot be expressed in polynomial equation form, therefore degree is not defined. Is how we understand the degree of a differential equation is not defined because it cannot be expressed in the polynomial form. For degree to be defined, the given differential equation must be in the polynomial form, whereas in this case it is not in polynomial form. Hence, though order is 2 which is defined, the degree is not defined. Is how we understand the limitations of differential equations with respect to order and degree.